Okay, this second video for 701 is going to cover a couple word problems. Let's do our first one. A population grows exponentially according to the differential equation dp over dt equals k times p, where p is the population, t is the time, k is a positive constant. If p of 0 equals a, that's a point where little t is 1 point, and then the value of p equals a. It's kind of funky looking. What is the time for the population to double its initial value? So this is the initial because the t value equals 0 here. T is time. Okay, so we're given a differential equation. Let's treat this like everything else and separate the variables. So we're going to multiply by the dt, puts it over on this side, and then the p needs to go over here with the dp. So divide by p, multiply by dt. And k is a constant, remember. Okay, so now we can integrate both sides. 1 over p is a natural log, and k is a constant, so it's just kt plus c over there. Let's solve for p, which means we're taking the exponential function, raising everything to the power of e, and then that cancels out that natural log. You're just left with p, and now you have this as the exponent. Everything is the exponent. Let's do that trick again, where it's really multiplication of two bases here. And then e to the c power is just plain old c. Okay. So we were given this point. Let's make the t coordinate 0, and let's make the p equal to a. And let's solve for c. I know that looks crazy because a is not a number, but we end up getting a equals c because c to the 0 power is just 1. I'm sorry, e to the 0 power is just 1. So here is our general solution. We now know the value of c. So the question, at what time is the population going to double its initial value? Meaning this is the initial. We want this to double. So instead of it equaling 1a, we want it to equal 2a's. We want the population to be 2 times whatever this value was. So you now have a situation where you can solve. You're going to have k in it, unfortunately, but the a disappears because we're going to divide both sides by a right now. And you end up with 2 equals e to the k times t power. Now in this case, we need to solve for t. We're solving for the t. We have to undo the exponential equation. So over here, you undo the natural log with the e. We have to do this to undo. Well, we're going to have to take the natural log to both sides here. That's how you undo the e. So these two are going to cancel. You're going to be left with kt on the right-hand side, and then the natural log of 2 on the left-hand side. And now you can just divide by k, and that's as far as you can take this one. Okay, our next one is our Newton's law of cooling example. The temperature of a pan of hot water varies according to Newton's law of cooling with that differential equation d big T, d little t. Big T is the water temperature, A is the room temperature, and K is a positive constant. If the water cools from 100 degrees Celsius to 60 degrees Celsius in 12 minutes at room temperature of 23, how long to the nearest minute will it take for the water to cool to 30 degrees Celsius? Okay, step one is let's deal with that differential equation. They gave us the room temperature of 23, so I took this A and I replaced it with a 23. So we're going to deal with this. We have to separate the variables. K is a constant. I'm going to multiply by the dt, but this t minus 23 goes to the other side by division. So that's our next step. And before you can integrate this, technically can't integrate the way it looks. If it was 1 over t, then it's natural log. But you have to use substitution here, where u is the t minus 23. And the derivative is really just 1. So 1 dt, this is 0. So we can replace this with a du and this with the u. And you end up with 1 over u du. That is a natural log. You can't just integrate this. Technically, there's substitution going on. And you end up with the natural log of u. This, again, is a constant, so this is negative kt. And then you have the plus c over here. Let's put the u back in. This is really t minus 23. Okay. Next step is to get the t by, we're going to solve for t. So let's raise everything to the natural log again. I'm sorry, raise everything to the e power again. Undo that natural log. So you're left with the t minus 23 on the left. And then this is all the exponent on the right. Again, this is when you have two pieces and an exponent being added, it's really the base, two bases being multiplied. And then this is that c. Just put it out front. And let's add 23. Okay, so this is our general equation for the cooling of the temperature of our water, hot water. Now, from here, there's a few things that you were given, but not directly. You were given the initial condition of the water, meaning it cooled from 100 degrees to 60 degrees in 12 minutes. There's 2 points there. It started out when t equals 0 at 100 degrees. And then at t equals 12 minutes later, it's 60 degrees. There's 2 points that were given to you right there. And then the question is asking how long, meaning we're going to be solving for little t, for the temperature to be 30, that's big T. So here's what the question is asking. We're eventually going to have to answer this. But right now we have this general equation that has 2 unknowns in it. So we need to figure out what those 2 unknowns are. We need to find C and we need to find K. So we can eventually set big T equal to 30 and then just solve for the T. The only thing left will be to solve for was T. So we have to undo, or we have to figure out what the C and the K are first. So we're going to use these 2 first. And let's start out with the initial, because if you plug in little t equals 0 right here, it'll make this whole thing equal 0. It gets rid of the k and will allow us to solve for c. If we use the 12 and the 60 first, we'll have a 12 here, we'll have a 60 here, we still have c and k. It doesn't help us find out what c and k are. So use the initial first because it gets rid of the k momentarily so we can find c. So let's do that real quick. So big T equals 100, little t equals 0 here. So that is c to the 0 power. This whole thing just equals 1. And if you subtract 23, you end up with c times 1 equals 77. So now we have c. We know what c is. Let's go back to this equation and replace it. Done. Okay, so our next step is to find k. Let's use the 12 and the 60 now. Plug in a 12 for the t, little t, and then plug in a 60 for the big T, and we'll be solving for k now. So subtract the 23, and you have negative 12k as your exponent. Let's divide by 77 next, so we can get that e term all by itself. And now at this step, if you want to undo an exponential function like this, we have to undo it with a natural log. So natural log to both sides, it's going to cancel out that e, and we're going to have negative 12k on the right-hand side, and the natural log of 37 over 77 on the left. And we're just going to take that natural log and divide it by negative 12. It's an icky decimal, rounded. Okay, so now back to our general equation that we found C, we're going to plug in K. Okay, let me recap. This is a long one. Look at all the steps on this page. We started out with a differential equation, and through some substitution here, we were able to get a general solution. And then using that given point, the initial condition first, we plugged in our 0 and 100 for the little t and the big T, and that allowed us to solve for C. So then once we have C, we use the other point, plugged it in for little t and big T. This allowed us to solve for K. So now our last step is to answer the question, which is how long will it take for the temperature of the water to be 30 degrees Celsius? Meaning the big T is equal to 30. What is the little t? These are only two variables left. So we can set the whole thing equal to 30 and then solve for t. So let's do this on the next page. Set the whole thing equal to 30, solve for t. We're going to subtract 27 and then, 23 and get 7 and then divide by this 77. And now this is that same rule again. If you want to undo the exponential equation here, you have to do the natural log to both sides. And when you do that, natural log here cancels. You're left with just that on the left, on the right. And we can divide the natural log of 7 over 77, or 1 over 11 if you want to simplify, divided by that negative number, and you get approximately 39 minutes. It's said to the nearest minute, so I rounded.